In this video, we'll learn about the Hammond Postulate. When we're looking at the Hammond Postulate, that really is a way to explain what a transition state might look like. So the structure of our transition state resembles the structure of its nearest stable species. So transition states for endergonic steps, the structure usually represents the products. And transition states for exergonic steps usually resemble the reactants. So our endergonic or endothermic ones usually resemble the products because the transition state is closer in energy to the product. For our exergonic or exothermic reactions, the transition state usually looks a lot closer to the reactants. So remember that transition state is the point at where the bonds are being made and broken at the same time. So it's not a state we can actually isolate. We can just speculate and hypothesize what it might look like. And so when we're looking at it, any 2 points on the energy diagram that are close in energy should be similar in structure. So if I have my reaction here where we have our methyl group, and I have a bromine on it, and then a chlorine is going to come and switch spots with the bromine. So that chlorine will come and attack the carbon and kick out the bromine to give us our product, where now we have our methyl group with the chloride, and then the bromide ion is floating in solution. So in the process of the arrows attacking here, in our mechanism, in the middle of it, when this is actually happening, the transition state would look something like this, where my bromine is starting to come off and my chlorine is starting to attach. So that's what the dashed lines here are. They're partial bonds. They're not quite full bonds. The electrons aren't all set in place yet. But so the more we move up the energy diagram, the weaker and weaker that bromine bond becomes, and the stronger the chlorine one is, till we have a 50-50 split, just like we see here. And then the further down we go, the weaker the bromine bond, the stronger the chlorine is, till the bromine is kicked out completely and the chloride has formed its full bond. So what our Hammond postulate says is, since this transition state is closer in energy to the reactants, my transition states should look a little more like a reactant. So it's not going to be completely 50-50. Instead, let's say we have our carbon. The bond to the bromine is going to be a stronger bond than that bond to the chlorine. So the transition state should have that bond to the bromine be somewhat of a stronger bond versus the bond to the chlorine, because the transition state here is closer in energy to the reactants versus the product. So that's really what Hammond's postulate says, is we can predict what that transition state should look like. And so looking at something exothermic versus endothermic, the faster reaction is the one that gives the more stable intermediate. So stability in this case is reflected in a lower energy transition state. So that means the one with the lower hump here, the lower transition state, is the faster reaction and gives the more stable intermediate. So if we took our 2-methylpropene and did this reaction, remember the carbocation, when we're comparing our 2 carbocations, the more stable carbocation has the one with more substituents. So that means if I'm looking at these two, I can predict that bottom line here, the green one, is to my tertiary carbocation. And then the red line, the one that has a higher energy of activation, so the slower reaction, is to my less stable carbocation, or the primary one. So this is how we can use our energy diagrams and predict which product we should get out of it. And this is why in this case, we get our regiospecific reaction to have the carbocation and the tertiary. That's why when we do the addition to our double bond, the halogen always adds to the more substituted carbon. And so we can use Hammond's postulate to predict what our transition states will look like and help predict which is the more stable transition state and therefore will give us the more stable product.